If you've ever made ice in one of those little rubber freezer trays, you may have noticed that if the water just goes to the rim of the tray, the ice will sometimes have expanded to be higher than that once it's frozen. And since pretty much all materials shrink as they cool down, this seems somewhat counterintuitive. Why is the ice a higher volume than the water? The answer is actually related to several other bizarre and very consequential properties of water. Now, this here is pretty much what a water molecule looks like. Now, atoms have a certain number of electrons that they normally have. So hydrogen atoms both have one each, and as far as we care, an oxygen atom has 6. It actually has more than that, but the rest of them lie dormant, not really doing anything. And atoms have certain numbers of electrons that they would like to have. So, for example, hydrogen atoms would like to have 2 electrons, and oxygen atoms would like to have 6 or 8 electrons. And so the way that these atoms solve this is by sharing their electrons with other atoms. So in water, each hydrogen atom shares its electron with the oxygen atom, and the oxygen atom shares one of its electrons with each hydrogen atom. And the hydrogen atoms both get to include the one that they're sharing with the oxygen atom and the one that the oxygen atom is sharing with them. So the hydrogen atoms get to act like they have 2 electrons. The oxygen atom gets to act like it has 8 electrons. The other side of this coin is that this bonds the atoms together, making them a molecule. Now, the shape of these bonds in a water molecule is basically a V like this. And this is important because this V is actually a spring. It behaves like this when force is put on it. And what this means is that as water molecules vibrate around, they collide with each other, and they basically compress their little spring shapes. And temperature, or heat or temperature, is basically a measurement of the momentum of the bouncing around of atoms or molecules. So as these molecules bounce around, they have a certain amount of momentum that they are doing that with. And that momentum is what we see as or feel as heat. And basically, when these molecules have a higher momentum, they bounce off of each other harder and they compress the springs more. They're also bouncing off of each other, and basically they have more momentum, so they have a higher internal pressure, so they want to be farther apart from each other. And when they're cooler, they don't really have as much energy, so they can be closer together. But for water molecules, what this also means is that there's less force on these springs. So when the temperature is higher, the springs are compressed by all the collisions, basically, and when the temperature is lower, the springs expand back outward. So for water molecules, even though the pressure of these molecules lowers with the temperature, the size of the molecules actually expands because these springs decompress as the temperature and pressure gets lower. And how this happens to work out is that around 0 degrees Celsius is when this effect is most pronounced, which is also when water freezes into ice at Earth's air pressure. So basically the molecules in ice aren't bouncing around very much. They're not colliding and compressing those springs, so the molecules expand outward more, even though they're not being forced apart as much. So overall, the same mass of water actually expands outward. Now, these springy little electron bonds are responsible for another interesting effect that water has. So if we have a group of water molecules like this, these hydrogen atoms will actually form their own little, basically, mini bonds with each other. And what these bonds do is absorb energy. basically forming these bonds is like falling down a hole, and the two hydrogen atoms fall down to the hole together, and that's when they're bonded together. But to break the bond requires a certain amount of energy. And what this means is that to raise the temperature of water, which requires basically forcing these atoms apart to make them less dense and higher pressure and to be able to vibrate around more, you need to break some of these hydrogen bonds so that the atoms are more free to move around. But breaking these hydrogen bonds takes a lot of energy. So in order to raise the temperature of water by 1 degree Celsius, you actually need more energy than to raise the temperature of, say, rock. And all materials have some amount of energy that they need to raise their temperature by 1 degree. And this is called their heat capacity, or the number itself is the specific heat of a material. So, for example, the specific heat of water is around, pretend that's a 4.18. And for, say, a rock, it's around 1.522. So if you pumped the same amount of energy into water as an equivalent mass of rock, you would actually raise the temperature of the rock by about 2 or 3 times as much as the temperature of the water. And this is why the oceans are so cold, because they're absorbing the same amount of energy from sunlight, but because it takes much more energy to raise the temperature of the water, to break these hydrogen bonds so that they can move around, the water doesn't raise its temperature as much as the rock does. And then when night comes and the sun is no longer inputting energy, it is much easier for the water to release energy, to form these hydrogen bonds, and so the oceans cool down faster. Overall, this means that the oceans are generally, and will pretty much always be, colder than rock will. And this is also why swimming pools are cool, because literally and figuratively, because the water is absorbing the exact same amount of energy as the concrete or whatever material is around it. It's just not heating up with that same amount of energy. So it feels cool. And because heat transfer is based off of the temperature of something, not how much energy, just raw energy it has, this is very convenient for cooling off wimpy humans who are too hot in the summer. Now, water is the common material with the highest specific heat value. It can absorb the most energy. But it does not have the highest specific heat value of any material. So the ones that have higher heat values or specific heat values are the atoms that are first on the periodic table of chemical elements. And the reason for this is that these atoms basically are small and simple enough that they behave something like bouncy balls. So they're just constantly bouncing around, and they can absorb a huge amount of energy, even though they're just still bouncing around like crazy. They can absorb a lot of energy. And so the materials that have very, very high specific heat values are lithium, which when it is solid, it has a specific heat value of 3.6, and when it's liquid, it has a specific heat value of 3.4. Basically, the change is that when it's solid, the atoms can't bounce around as much, and when it's liquid, they can. And when it's gaseous, it also can, and when it's gaseous, the specific heat value is only around 4.5. There isn't a huge change in between those. So lithium has a very high specific heat value because of its bouncy ball atom ability to absorb energy. But lithium is atom number 3 on the periodic table. Atoms number 1 and 2 are hydrogen and helium. And gaseous helium has a specific heat value of about 5.2. And it's the same reason as lithium. The atoms are basically bouncing around like bouncy balls or tennis balls, capable of absorbing huge amounts of energy without actually changing their state much. And gaseous hydrogen has a specific heat value of an incredible 14.3. And that is the highest specific heat value of any material, and probably of any material that can exist, aside from maybe some fun physics phenomena that haven't been fully worked out or discovered yet. But a side effect of this is that hydrogen and helium only have very high specific heat values when they are gases. When they are liquids, they behave more normally. Now, the other material, and it's a bit of an oddball, that has a very high specific heat value is ammonia. And ammonia is one nitrogen atom and a bunch of hydrogen atoms, like this. It's basically nitrogen's equivalent of water. And when ammonia is solid, it's not really special at all. And when it's liquid, it has a high specific heat value, but nothing like what water is capable of. But when it's gaseous, these hydrogen atoms basically begin acting like springs in a somewhat similar manner to how water does. And so these ammonia molecules are somewhat bouncy. So gaseous ammonia at around 200 degrees has a specific heat value of around 4.7. But because this is very temperature dependent, because of it needs the basically high heat and high vibration speed and springiness of the hydrogen atoms, this only works for ammonia when it's at a high temperature. When ammonia is at 100 degrees instead of 200 degrees, it only has a specific heat value of around 2.5. And when it's 0 degrees, it's something like 1.2. Now, water actually has kind of a similar thing to ammonia, although it isn't quite as extreme. Because the high specific heat value of water is dependent on the water molecules forming hydrogen bonds with each other, this only works when it is liquid, because it's only when it's liquid that both the atoms are moving around, or the molecules are moving around enough, but also close enough. When it's gaseous, they're just too far apart from each other to form many of these bonds, and when they're solid, they're both not moving around much, and it's pretty much all of the molecules are bonded together. So steam and ice both only have a specific heat value of about 2.1, or half of what water does. And this is a bit less of a coincidence than water's expanding ability. It's basically just that when water is liquid, it's just the right conditions for very high energy absorption, and when it's gas or liquid, it doesn't have those conditions present anymore. Now, if all this talk of specific heat values is seeming kind of theoretical to you, I will give a practical example in cooking. Because say you are boiling some water and cooking, say, a pork chop or a steak, the animal flesh that steaks and hamburgers and pork chops and delicious Eastern European sausages are made out of has a specific heat value of around 1.9 to 2.3. So the meat does not require very much energy to heat up quickly. So you can cook meat in a pan somewhat quickly. But in order to boil water, the water needs to absorb over twice as much energy to get to the same temperature. So getting it to that 100 degree threshold takes an insane amount of energy. But because its high energy absorption is dependent on being a liquid, as soon as it gets kicked over the threshold to being gas, it suddenly has a relatively normal specific heat value and heat absorption capacity, and its temperature spikes up incredibly quickly. So that is how the hydrogen bond springiness of water causes it to freeze the wrong way and be able to absorb ridiculous amounts of energy in changing temperature, which is what makes boiling water such a pain. I hope you enjoyed this video. Thank you. Have a nice day.